Okay, so now I want to talk about alkanes and cycloalkanes. So alkanes and cycloalkanes are hydrocarbons. Hydrocarbons are a class of compounds that contain only carbon and hydrogen. And there's really, we're going to look at saturated hydrocarbons in this unit. A saturated hydrocarbon is a hydrocarbon that contains only carbon-carbon single bonds. Okay, an alkane on the other hand, it's also a saturated hydrocarbons, and its carbons are arranged in either branched or open chains. Okay, and the alternative names for these alkanes are, they're also called aliphatic hydrocarbons. Okay, so now there's actually different classes of hydrocarbons, and remember, hydrocarbons only contain carbon and hydrogen atoms. So the first classification is between saturated and unsaturated. The saturated hydrocarbons is carbon, it only contains carbon-carbon single bonds. And again, each carbon is bonded to 4 other atoms. So this class of hydrocarbons is called alkanes, and we're going to investigate alkanes a little more. So here's an example of an alkane, ethane. Okay, so there's around each carbon atom, there's 4 single bonds, okay, and there's only carbon-carbon single bonds, okay. The other class of hydrocarbons are unsaturated hydrocarbons. So unsaturated hydrocarbons contain alkenes. Now alkenes contain 1 carbon-carbon double bond or more. So here's a structure of a simple alkene, ethene. Okay, and so each carbon atom has 3 electron groups, okay, and there's a carbon-carbon double bond. So we'll get into this, but in ethenes, the hybridization on these central carbons is sp2. And going back to the alkanes, the saturated alkanes, the hybridization scheme on the carbons is sp3. So we have, as far as unsaturated hydrocarbons go, we have alkenes. We also have something called alkynes. So alkynes actually contain 1 or more carbon-carbon triple bonds. So remember that a carbon-carbon triple bond, the carbon involved in the formation of that triple bond, each carbon has orbitals that are sp hybridized, and the geometry about that carbon in these alkynes is linear. In ethene, the geometry about the carbons is trigonal planar, and of course, going back to the ethane, the alkanes that contain carbon-carbon single bonds, the hybridization around every carbon is tetrahedral. Now, the last class of hydrocarbons we have are called arenes, or aromatic hydrocarbons. And these type of hydrocarbons, they're somewhat special. They're special in a sense that you have several different resonance structures, 2 different resonance structures. So you have the electrons localized on the ring. So again, these are called arenes, or aromatic hydrocarbons. Okay, so we said that alkanes, again, alkanes, the carbon only contains carbon, alkanes only contains carbon-carbon single bonds, and each carbon are sp3 hybridized in a tetrahedral type of arrangement. So that would mean the angles, the bond angles in an alkane, the carbon-carbon bond angles, and both the carbon-hydrogen bond angles and the hydrogen-carbon-hydrogen bond angles, they're all approximately 109.5 degrees, the geometry of a tetrahedron. Okay, so The electronic geometry about each carbon is tetrahedral with 4 single bonds, and the molecular geometry about the carbon atoms in the alkane are also tetrahedral. Okay, so we have several different ways of showing an alkane or showing the structures of alkanes. Okay, so we have we call different structural formulas. So the first one here, we have what's called the ball and stick model, which is aesthetically pleasing and kind of artistic, but difficult to draw by hand. So we have 2 other, of course we can also draw Lewis structures, but usually drawing all the single bonds in an alkane, even the carbon-hydrogen bonds would take a long time. So there's 2 other ways that we represent the structure of alkanes, and one of those ways is called the line angle formula. So in the line angle formula, we draw the ends of the lines denote a carbon atom, and where there's a vertex, okay, that denotes a carbon atom, another carbon atom. So you see, so there's this line angle formula basically means there's 1, 2, 3 carbons, okay, in this compound. So this is called propane. Now, in these line angle formulas, the hydrogens, we don't draw the hydrogens, but you can determine the number of hydrogens on each carbon because you have to, it only contains carbon and hydrogen, and each carbon has to contain 4 groups or 4 bonds surrounding it. So there's 1 carbon-carbon double bond, a single bond for this carbon at the end. So that means there has to be 3 hydrogen-carbon single bonds. So we can determine the number of hydrogens without writing them. On this middle carbon, okay, this middle carbon's bonded to another carbon and another carbon. So there's 2 bonded groups, single bonded groups. And to get 4 single bonded groups, we'd have to form 2 single bonds with hydrogen atoms. So there's 2 hydrogen atoms implied at this point here. And then of course there's 3 hydrogen atoms at the end. So this molecule here, butane, we have 1, 2, 3, 4 carbon atoms, and then likewise we can determine the number of hydrogens. And then pentane, we have 1, 2, 3, 4, 5. So again, these are line angle formulas, a very abbreviated way to represent the structures of these alkanes. Okay, so at the end, one thing to notice is that at the end of the chain, we know that we have to have a carbon with 3 hydrogens. This is called a CH3 group, or usually it's called a methyl group. Okay, and then we said that each vertex, you know, in these structures, each a vertex, and a vertex is here and here. There's a vertex here, and then a vertex, 1, 2, 3 vertexes. So those vertexes also represent a carbon atom. Now, another way to draw the structure of these compounds in organic chemistry is through something called condensed structural formulas. So what we do is we draw each carbon as a unit with its bonded hydrogen atoms. So at the ends, there's this CH3, this methyl unit, and then in the middle, these middle atoms, you have these carbons with 2 hydrogens. So we write CH3, CH2, CH3, and it's known that the carbons are bonded, even though the bonds aren't shown in the condensed structural formulas. You know from the general structure of alkanes that they contain carbon-carbon double bonds and then carbon-hydrogen bonds. So this carbon here is bonded to 3 hydrogen atoms. there's a single bond, carbon-carbon a carbon-carbon single bond between this carbon and this carbon, and then there's another carbon-carbon single bond between this carbon and this carbon. We can do the same thing for butane, draw the methyl group and then the two middle carbon atoms, and then the terminal methyl group. And then we can even add more of these CH2 groups to form a longer chain. And this is the condensed structural formula of pentane. All right, so the general formula for an alkane is C sub n H2n plus 2, where n is equal to the number of carbon atoms, and then 2n plus 2 is the number of hydrogen atoms. So if you have the simplest carbon atom C1, the simplest alkane, then the number of hydrogen atoms in that alkane is 2 times 1 plus 2, or 4. So the simplest alkane has a formula CH4, and that's methane. If we keep moving on, C2H6. Okay, we put the 2 in here, we're going to get C2H6, and that's called ethane. So what we can do is we can now start writing the condensed structural formula. There's a carbon-carbon double bond, and then there's 3 carbon-hydrogen single bonds attached to these 2 carbons. Okay, now C3H8. So the next one is propane, and again we can write a condensed structural formula. Now C4. Okay, so if we go C4H10 now, we get to butane. But notice that we can even simplify the condensed structural formula, because for butane, we could write CH3, CH2, CH2, CH3. We can put in all the carbon and hydrogen. We can put all we can put the unit of the carbon hydrogen units in these condensed structural formula, but you know that you're going to have 2 of these identical CH2 units in butane. So what you can do, instead of writing them all out, you can put CH2 underscore 2 twice. Okay, and the same thing with pentane, because you know you're going to have 3 intervening CH2 groups. So you would put the CH2 groups in parentheses in 3. So again, the number of carbons, 3 carbons here, 4, 5, that adds up. Okay, that's going to add up to 5 carbon atoms. Okay, so generally these are the unbranched alkanes. So it starts with methane, ethane, now propane, and butane. Now when you get to the alkanes, the longer alkanes past butane, then you start using Latin prefixes, like 5 is pentane, 6 hexane, heptane, octane, nonane for 9, decane, undecane, dodecane. So these, so you can see that once because of this formula, you can write these condensed structural formulas. So these lighter alkanes tend to be gases to propane. Then butane to nonane are liquids at room temperature, and these larger hydrocarbons or alkanes are usually solid, waxy-like substances. Okay, I wanted to talk a little bit more about these line angle formulas. So just to review, here's the line angle formulas for propane, butane, and pentane. They're straight chain alkanes. So remember that at the ends of the line angle formulas, at the 2 ends, there's always a carbon. It's not written with the C, but it's always there, and that each vertex is a carbon atom. So for propane, for example, you have one first carbon, second carbon, third carbon. For butane, 4 carbons, the first carbon at the end, second, third, fourth, the fourth carbon or the terminal carbon at the end, and then the fifth alkane, straight chain alkane, pentane, we have 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. That's fine, but notice that we don't specify the hydrogen atoms in the line angle formula, just the carbon chain. So what we can do is we can use the following rules to actually determine the number of hydrogens bound to each carbon. Okay, so now remember, each carbon remember, alkanes only contain carbon-carbon and carbon-hydrogen single bonds. So each carbon, to satisfy the octet rule with 4 single bonds, okay, the carbon must have 4 single bonds in a tetrahedral arrangement. So this carbon here at the end has to have an octet of electrons. It has a carbon-carbon bond already. That means it has to have 3 other single bonds with hydrogen atoms. So there's 3 hydrogen atoms located at this end and 3 hydrogen atoms located at this end. So how many hydrogen atoms will be located here in this vertex? Well, there's 2, 3 carbon-carbon double bonds, but then you have another 4th carbon-carbon double bond. So to make 4 single bonds, you would add, there'd be a hydrogen atom here. So you don't explicitly need to write the number of hydrogen atoms in these line angle formulas. You should be able to determine the number of hydrogen atoms. So for this carbon here at this vertex, there's 2 carbon-carbon single bonds to that carbon, and that means to get a total of 4 single bonds, you have to have 2 carbon-hydrogen single bonds. So there's 2 hydrogen atoms bound to here, and at the end there's 1 carbon-carbon double bond, so that means you usually have 3 hydrogens. So at the ends of the molecule, you usually have 3 hydrogens. If you have a branch point, the carbon at that branch point contains 1 hydrogen, and then if you're at the vertex of a straight chain alkane, you have 2 hydrogens. Now there's another rule that you can figure this out. So there's the number of visible bonds to each carbon, you take 4 and subtract that number of bonds to each carbon. So that would be 4 minus 1, 3 carbons. There's 2 carbon bonds here to this, 2 carbon single bonds to this carbon atom here. So 4 minus 2, 2 hydrogens. And then there's 3 carbon-carbon single bonds that this carbon here in the middle is involved with. So then there's 4 minus 1. So there's 1 hydrogen atom at this carbon here. Okay, so what I would like to do now are some examples of converting between condensed structural formulas and then line angle formulas for each of the alkanes. So let's go through I want to go through some of these, some of the problems, or some problems here, or some examples here on the whiteboard. So I will do that now. So I'm going to share the whiteboard screen here. All right, so I'm going to draw a condensed formula for a hydrocarbon. So the first example here, I'm going to draw the following structure, and then we're going to convert it into a line angle formula. So we have CH3, CH2, CH, here we have CH2, CH3, okay, CH, CH, CH3, 2, CH2, CH, CH3, and then we have CH3. So how would we draw a line angle formula for that? Well, we start at one end. We have a carbon-carbon double bond here, so we start here, right? Then usually what you do is you draw the next carbon as an angle, okay? Then at this carbon here, you have a hydrogen, but then you have a branch point. You have a carbon-carbon bond here, but then you have a carbon-carbon double bond, a carbon-carbon single bond here, and then there's another, on this group, there's another carbon atom here. So now we're up to here, and okay, so this carbon here, now, it contains a carbon atom here, and then this carbon atom actually is bonded to two methyl groups, CH3, so you have to have two methyl groups coming off that hydrogen. And you know that there's only one hydrogen here, so there has to be two other single bonds, and then those two single bonds involve this methyl group here. Okay, so this is a methyl group. So in organic chemistry, methyl groups are usually denoted by CH3. So where does that take us? So that takes us to, we were here, and then, see, I was off by one, I'm sorry. Okay, so the branch was next to, so this one would be over here, like this, okay, CH2, and now we're at this carbon here, so we go here, all right? Now we go to the next carbon here, and then we say there's a methyl group coming off there, one carbon at the end, and then we go to another methyl group. So now we have the line angle formula for this compound. This is the condensed structural formula, but now we have the line angle formula. And let's go and count and make sure we have the right number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We better have 13 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13. So this is the line angle formula for that compound. We'll do another example. Let's do this example here. CH3, C, CH3, CH3. So we have a carbon here. We have a carbon here with bonded to 4 methyl groups. So we start here, and then we have the carbon here. But then this is bonded to another methyl group here, and it's bonded to a third methyl group here. So, and then it's bonded to a fourth. So essentially, we would have a line angle formula that looks like that. You probably draw it with a cross like this. It looks kind of funny, but that's what it is. Okay, so let's do another one. So let's try this one here. CH3. 3CH. So that one here, we would start with this carbon here, and we'd start here, and we'd draw one methyl group, 2 methyl groups, and 3 methyl groups like that, because there's 1, 2, 3. The hydrogen's implied, so we would get the line angle formula like that. Let's try this one here, CH3, CH2, 3, CH, CH3, 2. So for this one, we have CH3, we have 3 of these CH2 groups. So we have 3 carbons that are straight chains. So we've got 1, 2, 3 here. Then we've got this carbon here, CH, but then that's bonded to 2 methyl groups. So that looks like that. So this is the condensed structural formula for that. Okay? So let me do another one. Let's do this one here. Let's see, did we do that one? Yeah, we did that one. So I'm going to do this one, CH3, CH2, CH2, CH3, CH2, CH3, CH2, CH3. So for that one, we would go, there's 2 carbons here, then there's a central carbon, and then there's another group here. So, and then there's another group here, and there's one more like that. So that would be this funny looking thing. Okay, so those are some examples. Those are some examples. Now, let's take some line angle formulas and then let's write the condensed structural formulas. So for that one, we're going to start with, we're going to be given a line angle formula like this, and then I'm going to write, okay, we're going to be given like that. Now to write the formula for this, there's a methyl group here and a methyl group here. So it's CH3, okay, and there's 3 hydrogens here. Then you go to this carbon here, and that has 1, that has to have a hydrogen, because it's got, and then that also is bonded to this carbon here. And then this branches into a CH here. Okay, there has to be 1 hydrogen here because there's 3 carbon-carbon single bonds to that carbon, and then there's 2 methyl groups coming off like this. Okay, so it would be better, we're going to clean this up a little bit, CH2, CH2, CH3. What we can do to clean this up a little bit is we can say CH3, CH, CH, and then we can say CH3, 2. We can put 2, we can abbreviate the methyl groups as parentheses with 2. Then what we can do is there's 2 of these identical CH2 units, so we can put CH2, 2, and then CH3. Okay, so this would be the final condensed structural formula for this line angle drawing here. So we'll do another one. So what if I gave you this formula here? Okay, so this one, let's start here, CH3, okay, and then this is bonded to C, this is like C, and then that's bonded to a CH3, and then that's bonded to CH3, another CH3, and then that's bonded to this carbon here, so we'll write the carbon here, and then that's got a CH3, CH3, CH3. And notice none of these carbons have hydrogen because they already have 4 carbon-carbon single bonds. All right? So if we write we can condense this further, and we can write CH3, 3C, and then we can write CH3, 3 like this. So that would be a condensed structural formula for that one. Let's do a few more. Let's see. Whiteboard. Clear. So the next one here is we're going to draw something like this. Okay, and that goes like that. That goes like that, like that. So what we can do here is we can write, first of all, we can write this carbon here, and then that one would have CH3, 3, and then we would go to the branch point CH, and then what we can do is we can write CH2, CH2, CH3, and we can write like that, okay? So that's one way to write that. If we wrote it, we can also write it something like this. This would be okay too. Okay, and then what we can do is move this up. We can CH, and then what we can do is we can write CH2, CH2, CH3, and then you'd also have a CH2, the same, like that. So we can write it like that. So we can do better than that. We can say CH3, 3, and then we can write CH here, and then we can write CH2, CH2, CH3, 2, which is basically, it's essentially what I've given you here. But if you wanted to, you could also keep this one, and you can write CH3, 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 CH, and then there's two of these. And then you can write CH3, CH2, 2, something like that. Okay, so there's several ways to write this one. Okay, let's go back to what happened to all right, there it goes, right? All right, so let's do, let's do one more. Okay, we're going to convert. So we're going to go, let's look at this compound here. So this one here, we can write CH3, start with CH3, CH2, CH2, CH, and then there's a CH3, a CH2, CH3. So we can write that one like that. Okay. Okay, so I want to share some examples of writing these condensed structural formulas, how to simplify them even further. So if we were given something like this. doing something like this. The question is how could we simplify this? Well, we have to realize that there's 4 of these CH2 units, and then there's 2 of these identical methyl units. So there's 4 of these CH2s and 2 of these. So what we can do is we can write CH3, CH2, and then there's 4 of them, then CH here, and then CH3, 2. So we can write even more condensed like that. How about this one here? H2, CH3, CH, let's see, H2, CH2, CH3, and then CH2, CH2, CH3. Okay, so the trick on this one is to realize that this group, these 3 groups are all the same. Okay, this is a propyl group called a propyl group. So what you can do is then take this middle carbon and then just write CH, a CH2, CH2, CH3, and then write 3. So we can write even more condensed abbreviated forms using of these condensed structural formulas using parentheses and subscripts. Okay, so now I want to talk about a very important concept in organic chemistry, and that's something called constitutional isomers. So constitutional isomers are actually groups of compounds with the same molecular formula but a different connectivity in their atoms. So that means that two or more constitutional isomers of alkanes, they have the same number of carbon and hydrogen atoms, but they contain a different bonding arrangement of the carbons, okay? So each bonding arrangement is a different compound. It has different physical and chemical properties, okay? Even though they have the same molecular formula, like C4H10. So, for example, butane, this is the molecular formula for alkanes with C4H10. Now, you can have an arrangement with this molecular formula where you have a straight chain alkane like this. You have butane here, okay? But you can also have the same formula. You can have you can have a chain of 3, and then the 4th carbon is comes off as a branch. So you have a branch chain molecule here, but they still have the same formula. Okay, but notice that this is called butane, and this is called 2-methylpropane. This has a much lower boiling point than this compound here. So these are constitutional isomers, but they have different structures, different bonding arrangements of the carbons. Okay, so those are constitutional isomers, and it's this ability of carbon to form many different constitutional isomers that results in an enormous number of constitutional isomers as the number of carbon atoms increases. So for one carbon atom, you would just, the simplest hydrocarbon would be methane. So you don't have isomers. Methane is methane. A methane molecule is a methane molecule. You can't arrange the carbons any different way because there's only one carbon, and there has to be the 3 hydrogens have to bond to that carbon. Now, but if you have 5 carbon atoms, you can have 3 constitutional isomers, and as you go up in number, as you go up in the number of carbon atoms, the number of constitutional isomers increases so rapidly because there's so many different more combinations of bonding. So if you go up to 15, you have over 4,000, and now you're up to 25, and you have almost 37 million constitutional isomers. So this is what makes organic chemistry interesting, because the carbon shows much versatility in its bonding, and then you have many, many possibilities for constitutional isomers. More constitutional isomers, or a greater number of constitutional isomers, the more carbon atoms you have in the structure. Okay, so as a exercise, let's draw the structure of all the constitutional isomers of an alkane that has 5 carbon atoms. So if we remember the formula for alkanes is C of N H2N plus 2. So if we have 5 carbon atoms, that'll give us the alkane corresponding to 5 carbon atoms will be C5H12. So how many different constitutional isomers can we get from C5H12? Well, we can have one where it's all, the carbons are all bonded in a straight chain. Okay, so we have that isomer. Okay, what if we created an isomer where we have one of the methyl groups attached to the first carbon instead of 2 hydrogen groups, and then we would have 4. So this would be another constitutional isomer. So this compound is called N-pentane. We'll get to nomenclature a little bit later. This is 2-methyl butane. Okay, because 1, 2, 3. Now you look for the longest main chain. Now, what if we had a compound where we put the methyl now? We put the methyl now on the 3rd carbon here. Well, that wouldn't make a big difference, because if we did that, we would have the same structure as this one here. So that really wouldn't be a possibility. Now, what if we did the following? What if we had, say, a 3 carbon atom chain, and then we, like this, and then what if we okay, so this one here, this compound here is called trimethylmethane. Okay. So this is a 3rd possibility. Now, what if we did the following? What if we did the following? What if we, so you have CH3, and then we can do the following. We can do something like that. CH2, CH3, and then CH3, like that. Although that would be the same compound as here, though. Okay, so these are the 3 constitutional isomers with this formula C5H12. Okay, so let's draw now all the constitutional isomers. Let me make sure. Let's draw the constitutional isomers of a compound with C6H14. Okay, all the constitutional isomers of that compound. Okay, and there's 5 of them. Okay, so there's 5 constitutional isomers. Okay, so we can draw the straight chain one. So we can draw like 1, 2, 3, 4, 5, 6. So we have six in the longest chain. Well, now what if we have 5? We have something with 5 in the longest chain. Okay? And what if we put a methyl group there? So that would be a second one. Okay? And 1, 2, 3, 4, 5. We can put the methyl group here, and that would be a second one, and then a third one. The third one we could put the methyl group here. Okay. Now, what if so these are the constitutional isomers where the longest chain is 5. And then we have these branched methyl groups. We have one branched methyl group. This here is the longest chain, the constitutional isomer where the longest chain is 6 carbons. 6 carbons. Okay, now what if we have a chain that's 4 carbons? Like this, 1, 2, well, we've got 1 too many. So we have 4 carbons, and we have to find a way to add 2 carbons. And we know they'd have to be branches. So what we can do is we can put say a methyl group here, and we can put a methyl group here. Okay, so that would be 1, 2, 3. I already made a mistake here. So this one, let's just start again with the 4. Okay, so I made 5 instead of 4. So we'd have 1, 2. So you'd have 1, 2. So you'd have 4, 1, 2, 3, 4 as the main chain. So what you can do is you can put a methyl group here, and you can put a methyl group right here. All right. Then what you can do is you can have one where you just put the methyl groups on the same carbon. Oh, this is tricky. What you can do is you can draw it like this, maybe. No, I don't like that either. How do we draw this? It's better to draw it, I think. It's 1, 2. So you'd have 3. You'd have 2 methyl groups here, and then 1, 2, 3, 4. I guess you could draw it. You can draw each vertically. You can draw it 1, 2, 3, 4. You can draw it like this. Yeah, usually you don't want to draw straight crosses. So in this 1, 2, 3, I have 1 too many carbons here. So shoot. So I get 1, 2, 3, 4. So it would be like that. Now notice because notice that if we put the two methyl groups here, okay, these two are identical compounds. They're just written in different orientations because we could rotate this one, this molecule, into this position and we'd have identical molecules, okay? So that's the thing about organic chemistry and drawing. You have to kind of get a feel for which drawings are identical representations of the same molecule. So likewise, what did I do here? See, I did something. Actually, there's a mistake here. I put the two identical molecules here. So we'd want, what we want to do is put the methyl group. 1, 2, 3. Okay, so we would want it 3. Wait, 1, 2, 3. Okay, that would be here. And then 1, 2, 3. Actually, we would want to put like that. And yeah, okay, so now see, this one here, you may ask yourself, well, why don't you just put, can't you just draw like this? But these are the same, these are equivalent molecules because you can rotate this molecule and get the same molecule, the same structure. So you have to remember that because of the, you have to remember there's an inherent symmetry in these molecules. Okay, so you may think that some line angle formulas are different, but you can rotate these separate formulas and you end up in the same, with the same structure. Likewise, this structure that I'm drawing here would be the same if you put, I believe if you put the, if you put it here, it would be the same as this one here. And then as far as this one goes, so this would be the this would be the same as this one. So that's why you only have 5. So these are the 5 constitutional isomers of C6H14. Okay, so we talked about constitutional isomerism. Now what I want to talk about is naming alkanes. So there's a way, a standard way of naming we said there's many different possibilities for constitutional isomerism. So we have a vast array of organic compounds, and that holds true for alkanes. So we can write the formula, either the condensed or the light, or the line angle formula, but it's convenient sometimes to write out the name of the alkane, and that goes for other classes of organic compounds too. So if you have straight chain alkanes, then well, not only straight chains, but you have to designate an organic compound that's an alkane. In the name will end with this ane suffix. So ane specifies the alkane, and then a prefix tells us the number of carbon atoms. Okay, so meth denotes 1 carbon atom, eth 2, prop 3, but 4, pent 5, hex 6, hep 7, oct 8, non 9, and then etc. Okay, so if you have a straight chain alkane with 17 carbon atoms, it's called heptadecane. Heptadecane. Let's go back to a previous slide. Okay. Okay, so here again, remember these are straight chain alkanes. Okay, so meth means one carbon and ane is an alkane. So for straight chain alkanes, we use the prefix and then the suffix aned. So if we go to the one with the example with 17, it's heptadecane. Okay, so that's pretty easy. Octane, 8 carbon atoms, and then we add the ane to denote it's an alkane. So that's straightforward for straight chain hydrocarbons. Okay, so what you have to do for, now you have straight chain alkanes, but in most cases you'll have a branched chain alkane. So the way you name those is if you're given a condensed structural formula, you look through this condensed formula to find the parent compound, okay, that you base the name on. So you're going to give it a parent name, and that's, so what you do is you find the longest carbon chain, and then you look for the branch substituents. And the branch substituents are known as alkyl group, okay? And you derive these substituents, you bond that substituent through a carbon to the main chain, okay? So an alkyl group is formed by the removal of the hydrogen atom from an alkane. It's usually denoted by the symbol R. Okay, so the alkyl group for meth, based on methane, becomes methyl. You add a YL, okay, to denote an alkyl group. The alkyl group based upon ethane becomes, you remove a hydrogen, and this group becomes ethyl, okay? So here's an example. So if you look at this compound, the condensed formula for this compound, you find the longest chain, and the longest chain is 1, 2, 3, 4, 5, 6, 7, 8. So the parent compound is octane, okay? And the substituent is this CH3 group. And we said that this is based on methane, but we it's based on methane, but we lose one hydrogen because we have to form a carbon-carbon bond now, and with the parent chain. So this becomes, this is a methyl group. So the name of this compound is 4-methyl-octane. And we're going to get to this. The 4 is because if we number the longest chain, okay, and we count over from the end, the alkyl group is bonded to the 4th carbon atom at the end. So that's why there's a 4-methyl-octane. Okay, so the methyl is the name of the alkyl group. It's attached to at the 4 carbon atom, labeled 4, of the parent compound with the longest chain, octane. Okay, so here's some names of some of the most common alkyl groups in these alkanes. And remember these alkyl groups are the branch off the longest chain or the parent compound. So we already talked about the methyl group based on methane. This is an ethyl group based upon ethane. You have a propyl group. Then you can have something called an isopropyl group, where you have 3 carbons, but it's bonded to, you take a hydrogen off this middle carbon atom of propane and bond it through the second. You bond this to the main parent hydrocarbon through the second carbon atom. And you can have a butyl group, and then you can have an isobutyl group here. This is based upon a constitutional isomer of butane. You can even have a secondary butyl group, and you can have this tertiary butyl group here. Okay, so you can have different possibilities for an alkyl group. Okay, so now we get into the actual rules, and this is called IUPAC nomenclature, Standard International Union of Pure and Applied Chemistry. So one day there was a big meeting, I think somewhere in Switzerland, where a group of chemists decided we're going to decide on some standard rules for naming organic compounds. So that's because chemists around the world can make sure that they're ordering the right, if they're in, if the names are standardized internationally and a chemist has to order compounds, he or she'll know that they're ordering the right compound. So the rules are: the name of an alkane with an unbranched chain consists of a prefix and suffix ane. We already went through that. And then we have this idea that we have a parent chain, and then we have the branched alkyl groups. And the parent chain is the chain that has the longest number of carbon atoms. Okay, and then each substituent, we give it a name and a number. Okay, so each branch, we give a name and a number. So here's the condensed structural formula here. This formula here, the longest chain is 1, 2, 3, 3 carbon atoms. Notice that it doesn't matter. We can still draw it. We can still count the third chain, 1, 2, 3. We can go this way. And then we can also say, well, the longest chain is this way, or the longest chain is this way. It doesn't really matter. They're both identical. But the way that they wrote it here with the H horizontal, it implies that you first identify the longest chain in the horizontal direction, but there's no reason why you can't go diagonal. So you number from one end, 1, 2, 3. You number the longest chain. Okay. Then you look where the alkyl group is attached. That's attached to carbon number 2. You give the name of the alkyl group. So what you do is you put a 2, the name of the alkyl group, 2-methyl, and then the name of the parent hydrocarbon. So 1, 2, 3, the parent hydrocarbon with 3, the parent alkane with 3 carbons is propane. So 2-methyl propane. Okay, so now here's when it gets more complicated. This is easy because you only have one substituent off the main parent chain, but you can have different numbers of more than one substituent off the main chain. So let's look at this example here. So the parent compound here, let's count 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. It doesn't matter if we go here this way or this way. So what we can, well, no, actually, let me correct myself. I'm jumping ahead. This compound here also has one substituent, but you may ask yourself, well, do we number the carbons with the 1 here, or do we number the 1 here with 1 here? Okay, so if we did it like this, we started at this end, 1, 2, 3, 4, 5, then we would give the name 2-methyl pentane. Okay, but what if we numbered from here, this end, 1, 2, 3, 4, 5? Well, then that would be 4-methylpentane. So we want to number the chain from the end of the parent chain that gives the number associated with the substituent the smallest number. Okay, so that's one of the rules. Okay. Okay, so now if you have a parent chain with 2 or more identical substituents, you number the parent chain from the end that gives the lower number of the substituent encountered first. All right, and then the number of times that substituent is found, You indicate that by Latin prefix, di for 2, tri for 3, tetra 4, penta 5, and so on. So let's look at this compound here. Well, let's identify the longest parent chain. 1, 2, 3, 4, 5, 6. So the parent chain, the parent alkane with 6 carbons is hexane. So this compound is based upon hexane. So the question is, do we number from this end or do we number from this end? Well, let's number from this end. 1, 2, 3, 4, 5, 6. Shown here. 1, 2, 3, 4, 5, 6. This is the line angle formula for this. Okay? So if we numbered it like this, the compound would be called 2. We put 2, and then for the first methyl, then we put a comma, then we put 4 for the second substituent, and they're identical, so we put di, and these are methyl groups, dimethyl 2,4-dimethyl hexane. All right? Now, if we numbered it from this end, 1, 2, 3, 4, 5, 6, the first group we encounter is at the 3 position. Okay, the third carbon position. So in the next methyl group, the second would be at the 5. So we would call that 3,5-dimethyl hexane. But if we number this way, the third carbon is, we encounter the first substituent. But if we number this way, this carbon number where we found the substituent, first substituent is lower. The 2 here where we find it is lower than the 3 if we number from this end. Okay, so this has a higher number, carbon atom number where we first encountered the substituent than this one here. So it's not 3,5-dimethyl hexane, it's 2,4 because we encounter the substituent first on a lower number, then numbering it from the left to right. Okay, so that's rule. Now it gets more complicated. This is the case where if you have 2 or more different substituents, here what we do is we list them in alphabetical order, and then what you do is you number, to decide the numbering, you number from the end of the chain that gives the substituent encountered first the lower number. It's like the previous rule. Okay, you number them, and you choose the right numbering when the first substituent has the lower number of carbons. So let's look at this example here. So the parent chain 1, 2, 3, 4, 5, 6, 7. So 7, the hexane with 7 carbons is heptane. So the parent compound is heptane. All right, and we have 2 substituents here. This is a methyl alkyl group, and then this is the ethyl. Okay, so E is lower alphabetical order than M, so the ethyl group name will go first. But the question is the numbering. Well, if we number from here, this end here, 1, 2, 3, 4, 5, 6, 7. And it's that the number 3 carbon where we encounter the first substituent. Now, if we number from the other end, we get 1, 2, 3, 4, 5, 6, 7. Well, we also encounter, it's the same thing. We encounter, we encounter 3 here, but we would keep this numbering here because the E, the ethyl, is the substituent first, and it has the lower, E becomes comes before M in the alphabet. So we'd have 3 ethyl dash 3 dash, put dashes, 3 ethyl dash 5 dash methyl heptane. So we wouldn't number it 1, 2, 3, 3 methyl, 5 ethyl heptane. Okay, so we use the numbering system because we get to the alkyl group that has the lower, it's higher in alphabetical order than the methyl group. Okay, so All right, so if you have, this is pretty, if you have prefixes di, tri, tetra are not included in the alphabetation, but iso, like isopropyl alcohol is, or isopropyl is included in the alphabetization, all right, and so are methyl and ethyl, okay? So let's try this one here. So the longest parent chain is 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So 6, there's like 6, the hexane is the main chain. So if we do the numbering, 1, 2, 3, 4, 5, 6. So if we numbered from this end, then the ethyl group would first come at number 3, okay? But the first substituent would come as number 3, but in this numbering system, the first substituent occurs at a lower number, number 2. So we number it from this end, okay? So these are 2 methyl groups, and we would call it dimethyl, but the di is not part of the alphabetization system. So then we go to the next one, which is ethyl. Now ethyl has a higher an E is higher than is in higher prioritization as far as alphabetization as an M in methyl. So we would first put 4 ethyl, then we'd say 2 dimethyl hexane. Okay, we don't put 2,2-dimethyl 4-ethyl hexane, even though we think D is lower in alphabetical, is the higher priority in alphabetical order, because you don't count the D. Okay. Okay, so we're going to start out by doing some examples using IUPAC nomenclature here. Okay, so let's see some examples of IUPAC naming IUPAC alkane, giving IUPAC name for alkanes. So let's do the first example. Let's do the first example here. Okay. So I'm going to have to, fortunately, let's H2CH3. Okay, so first we find the longest parent chain. So 1, 2, 3, 4, 5. So the parent compound is based on pentane, the alkane with 5 carbon atoms. And then we number 1, 2, 3, 4, 5. We number the carbons, and then we counter our first substituent, which is the methyl. So we say 2-methyl pentane. Okay, so that would be that one. We would not say, we would not number from here 3, 4, 5. If that were the case, we would have 4-methyl pentane. But we always want to use the lowest number, which is 2. Let's do this compound here. Okay, so the parent chain here, it's 1, 2, 3, 4, 5, 6 carbon atoms. So it's based upon hexane, the parent. And if we number here 1, 2, 3, 4, 5, 6, and if we number from here 1, 2, 3, 4, 5, 6. Notice the numbering this way or this way doesn't matter. So the reason being is if we number this way, then we have 2, and we have identical we have an identical substituent. So we put, the first time we get the substituent, a number 2 carbon, and then the second time is number 5. Then we put dimethyl, because there's 2 of them, methyl hexane. Okay, so that's if we number this way. But then if we number this way, we also get 2,5-dimethyl hexane. Okay, so the numbering, we can number from either direction and end up at the same answer. Let's do another one here. 2, 4, CH, CH2, CH3, CH2, CH3. So the longest parent chain is 1 carbon. There's 4 of these. So 1 plus 4 is 5, 6, 7, 8. So this is the parent compound. It's based on octane. Okay, so we number from here. So this would be 1. Then we have 2, 3, 4, 5. Because remember, there's 4 of these CH2 groups. So we have to include them in the numbering. 5, 6, 7, 8. Okay, so we have, if we number that way. And if we number the other way, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we do like that. Okay, so that one, if we did that one, that would be, if we did that one, we would get, if we did the numbering this way, we would get 1, 2, 3. So we get 3 ethyl octane. Okay, now if we numbered it this way, then the ethyl group would wind up on number 6. And that's not what we're really, we have to use the lower number. So that one would be 3 ethyl octane, not 6 ethyl octane. Okay, let's continue our discussion of IUPAC nomenclature. So now we're going to do a little variant of the examples we gave. I gave you a structure, and we looked at, we went through how to name those structures. Here's an example where I'm going to give you a name, and we're gonna try to understand. This name is incorrect, so we're going to try to understand why and then write the correct name. So the incorrect name here is 1,3 dimethyl butane. So let's try to work this out. So 1, there's a methyl group here. 1. So if that were the case, 1, okay, so 1 would be here. 1, 2, 1, 3. Dimethyl, 1, 2, 3. 1, 2, 3, 4. Okay, so 1, 2, butane is the parent, and then according to here, we would name it 1, 2, 3, 4. 1, 3 dimethyl butane. So there's, so is that right? No, that wouldn't be. I'm sorry. So it would start. So the 1 would be. Okay, this is So this would be, according to this, the way it's written, this would be 1, and then you'd have a methyl group off the 1. This would be 2. This would be 3. So then you'd have the methyl group. Off of this this carbon here. 1, 3, 1, 2, 3. And then you'd have 4 here. So why is this incorrect? Well, the reason it's incorrect is because really the longest chain would be 1, 2, 3, 4, 5. It would really be 5 carbons. Because a 1 in the methyl group, in the 1 position, the methyl group is really part of the main chain. Okay, you would follow the main chain. So the proper name for this compound would be, you would have to move, say, the one possibility is 1, 2, 3, 4, 5. It would be, you would number from this way, and then it would be 4-methyl pentane. The parent compound then would be 5 carbon, so it would be pentane. Okay, but if we number it from the left to right, then we would have a 4 on the methyl group. So remember, we number it so that the substituent coming off the main chain has the lowest number. So 1 through 3, 4, 5. So the proper name then would be 2-methyl pentane. Okay, so that would be the proper formula. And while we're on this compound, let's do the line angle formula for this one. 1, 2, 3, 4, 5. So here's the main chain, and then the methyl group is at position 2, which is right here. So this is the line angle formula for 2-methyl pentane, right? So let's do another example. The next example is 4. So this is A. B is 4-methyl pentane. Okay, so this is related to the one we just did above here. So 4-methyl pentane would be, it would just be, if we numbered this compound pentane from left to right with 1 here, the 4-methyl pentane would be here. We'd name it 4-methyl pentane. But we have to number it from right to left because we want the first carbon encountered, the lowest number for the first substituent would be 2 instead of 4. So that's why it would be, instead of 4-methyl pentane, we want 2-methyl pentane. Okay, so we could also, instead of drawing the structure like this, we could also draw it 1, 2, 3, 4. We can also draw it 2-methyl pentane like this. These two are the same structure, okay? Because just think, if you flipped this molecule this drawing 180 degrees in the plane of the paper, you'd end up with the same molecule. You're not making or breaking any bonds by rotating it. So let's do another one. All right, so now we have 2,2-diethyl butane. So an ethyl group has this, the ethyl substituent has this structure here. Okay, so butane is the parent hydrocarbon. So butane contains four carbons. Okay, so 2,2-diethyl would be, this is 1, this is 2. So the 2,2-diethyl would be an ethyl group, 2 ethyl groups bonded to carbon number 2, like this. And then we have no hydrogens attached because there's 4 carbon-carbon bonds to this carbon here, this number 2. So 1, 2, 3, 4. So this is 1, 2. This would be the structure. If we wrote the structure corresponding to this name, this would be it. But the question is now, why is this not correct? So the reason this isn't correct is the following. If we number 1, 2, 3, 4, so we have the chain, this chain here. Okay, this chain here, we'll just make a chain as an arrow. That has 4 carbons. Now this chain here, this way and this way, also have 4 carbons. But if we start the beginning of the chain here, we have 1, 2, 3, 4, 5. So if we go numbering, if we follow the chain along this direction from one end, we have 5 carbons. So the parent compound is not butane, it's but pentane. Okay, so let's redraw it. Let's redraw it from here. Well, let's just draw it from this end. So it would be CH3, CH2, C, like this, CH2, CH3. So we use 1, but then there's still, we follow this way, but then there's still there's still one methyl group, one ethyl group, which we can put here. But then now there's this methyl group like this. So this is really the proper, the proper way that will best, well, this is correct too, but the way to write this, we won't make this mistake on the nomenclature, or we can understand why this nomenclature is incorrect. So in this case, you would have, if you've numbered here, you'd have 1, 2, 3, 4, 5. And if you numbered from this way here, 1, 2, 3, 4, 5, both substituents are on the number 3 carbon atom, whichever way you go. So the question is you have a single methyl group and you have a single ethyl group. So the ethyl comes first in the alphabet. The ethyl substituent comes with the letter E, becomes first, starts with the letter E, comes first, then the methyl substituent, which starts with the letter M. So the ethyl substituent is named first. So we say 3 ethyl, and we put a dash here, and then we say 3 methyl, and then the parent hydrocarbon is pentane, so we say 3 ethyl, 3 methyl pentane, like this, okay? Now, if we draw the line angle formula, let's draw the line angled formula. So we have carbon 1 and 2 here, we have carbon 3, okay? And there's an ethyl group and a methyl group, okay, from here. And then here's number 4 and number 5. So we can draw a line angle formula for this compound, and it would look something like this, okay? So let's do a few more. So the next substituent is not substituent, but the next example is 2 ethyl, 3 methyl pentane. A 2-ethyl 3-methyl pentane. Okay, well, let's see what's going on here. So the parent is pentane. So we have, let's just start drawing the skeleton. So we have carbon 1 here, and then this is carbon 2. We have an ethyl group. And then carbon 3, we have a methyl group. And then we have the rest of the pentane. Okay, so why is this not correct? Well, that's a good question. So we have 1, 2, 3, 4, 5. Okay, so that's right. So if we number from this way, we'd have 1, 2, 3, 4, 5. Okay. Okay, so this is what we have here. Okay. Now it takes a little bit of examination, but we first look to see if we have the correct longest parent hydrocarbon, and I can see if we count number 1 here, 1, 2, 3, 4, 5, 6. So actually, we can fish out the largest parent hydrocarbon is not pentane, but hexane with 6 carbon atoms. So if we redraw the structure with this as the number 1 carbon from left to right, we would get CH3, CH2, CH, CH3, this carbon. Now we have CH, but we want the main chain to continue in this direction, so we would write the rest of these ethyl group horizontally, and then we would take the ethyl group here as a branch, CH2. When we rewrite it this way, we can better get at the nomenclature here. So 1, 2, 3, 4, 5, we have 6, a parent chain of 6. So let's figure out the numbering. So if we number this way, 1, 2, 3, 4, 5, 6. And if we number this way, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 1, 2, 3. So either way, we're going to get the same name whether we number from left to right or right to left. So really what we'd end up with is 3, 1, 2, 3, 4 dimethyl hexane. So this is the proper name for it. And if we draw the line angle formula, 1, 2, 3, we'd have a methyl group here, we'd have a methyl group here, and then we'd have 1, 2, 3, 4, 5, 6. So the line angle formula for this compound is here. Okay, let's keep moving on. All right, so okay, so 2 propyl pentane. Okay, so 2 propyl pentane. So let's draw the parent pentane, and then the 2 carbon is here, and what we would have is a propyl group. The propyl substituent has this structure. So it would be CH2, CH2, CH3, and so that's 2 propyl, 1, 2, and then the pentane, 2, 1, 2, 3, 4, 5. So I can think you can see why This is not correct because really the longest chain goes from 1, 2, 3, 4, 5, 6, 7. It's 7 carbons, not 5. So if we redraw this now, we would say CH3, CH2, we're going from here to here, CH2, CH. Then there's the methyl group here, which we'll put down here, and then we'll put the propyl group. Okay, so now what do we have? We have this representation here. And if we number from left to right, 1, 2, 3, 4, 5, 6, 7, we get the methyl group at the 4 position. If we renumber the alternate way, 1, 2, 3, 4, 5, 6, 7. So here, the numbering on the methyl group would be at position 4. And if we did it the other way, it would also be at position 4. So the numbering is the same in either direction. So this is called 4-methyl heptane. If you have 7 carbons, it's called heptane. Okay. And again, the line angle formula, 1, 2, 3, 4, and then we've got the methyl group here, 4, 5, 6, 7. So there's the line angle formula for 4-methyl pentane. Okay, so let's try another one. Okay, so 2 diethyl heptane. Okay, so again, the longest chain is probably not a heptane. So let's just start drawing. So 2, 2. So there's your 2 diethyl groups off number 2. And then we've got to put in 7 more. We have to make a chain of 7 carbons. We already have 2, so we have to add 5 more. So 1, 2, 3, 4, 5, like that. Okay, so, but the longest chain is not like we've written it. The longest chain would be looping around to one of the ethyl groups, which is 1, 2, 3, 4, 5, 6, 7, 8. It's 8 carbons. So the parent compound is octane, not heptane. So if we drew it, say starting here, and move that over here, CH2, C, there's still another ethyl group here we have to account for, and then there's a CH3, and then there's the 5 remaining. Okay, so it would be like that. And then in this case, it's clear that if you numbered from this direction, 1, 2, 3, 4, 5, you'd have 6 ethyl methyl octane. But if you number here, you have a 3 on the substituent, which is a lower number than 6. So we number from this direction here. So that would be 3 ethyl. E goes before M, 3 methyl. Octane. Okay, so this is the proper way to write this. And if we did a 2, 3, 4, 5. So that would be the line angle formula for that one. Okay, so okay, all right. So that's enough of examples for IUPAC nomenclature for now. We'll probably do some more later on. Okay, so now we were going to go over a way to classify carbons in alkanes. Okay, so a carbon atom in an alkane is either primary, shown here, secondary, or tertiary, or quaternary. Okay, so this is the definition. A primary carbon is a carbon that's bonded to only one other carbon. So this methyl carbon is bonded to only this carbon atom. It only has one bond to the other carbon atom. So this is a primary carbon in an alkane. This is also primary. This is primary, this is a primary carbon, and this is a primary carbon. Okay? Now a secondary carbon is one that's bonded to two other carbons. So this carbon here is bonded to this carbon to the left and this carbon to the right. So this here is a secondary carbon atom. And then this is the only example of a secondary carbon atom in 2,2,4-trimethyl pentane. Now a tertiary carbon is a carbon that's bonded to three other carbon atoms. So this carbon here has bonded to this carbon, this methyl group, this carbon atom, this secondary carbon atom, and then this methyl group here. So it's a tertiary carbon atom. And finally, a quaternary carbon atom is a carbon atom bonded to four other carbon atoms. So here, this atom here is bonded to 1, 2, 3, 4 carbon atoms. So this is a quaternary carbon atom. All right. So now the same goes with, there's also, this doesn't show this on the slide, but we also have primary, secondary, and tertiary hydrogens. So a primary hydrogen is a hydrogen attached to a carbon that is bonded to one carbon atom. So the hydrogens on these groups here are primary hydrogen atoms. The hydrogen atom is secondary if it's bonded to a carbon that's bonded to two other carbons. So these hydrogens here are secondary hydrogens, not hydrons, hydrogens. A hydrogen that's bonded to a carbon with three bonds to other carbons is a tertiary carbon. And then we don't have a quaternary carbon because there's no hydrogens that can be attached to a quaternary carbon because it already makes 4 single bonds to other carbon atoms, okay? So, so basically a hydrogen carbon bond on a primary carbon, that hydrogen in that bond is a primary hydrogen. A hydrogen associated with a secondary carbon is a secondary hydrogen here. And a hydrogen associated with a tertiary carbon is a tertiary hydrogen. Okay, so it makes, it's illogical. Okay, so let's do an example. Let's do an example of of identifying primary, secondary, and tertiary hydrogens or carbons and hydrogens. So here's an example. Let's write up an example. So here's an example molecule here, which I have to. There was a way to figure out how to. Okay, so we have, let's draw a line angle formula for this compound here. So that's, okay, so this is, what is the name of this? Let's see what we can call this. So the parent chain is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's the longest chain is 6 carbon atoms. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So, so let's see. Yeah. So this group here, okay, so we can write the condensed formula here like this. CH, CH3, CH, CH, CH3, CH3, CH, CH, CH2, 1, 2, 3, 4, CH2, CH3. So, so this is the isopropyl group. This is an isopropyl group. Remember, an isopropyl group like this. Okay, so if we do the numbering, this is 1, 2, 3, 4, 5, 6. It should be numbered from left to right because the first substituent, the methyl, is found on number 2. If we wrote it from right to left, the first substituent would fall on carbon atom 1 to number 4. So we number this way. This is an isopropyl group. This is a methyl group. I is before M in the alphabet. So we say 3-isopropyl, 2-methyl hexane. So that's our compound here. So let's decide the carbons. This is a primary carbon attached to one other carbon. This is a tertiary hydrogen or carbon because it's attached to 3 other carbons. This is a primary. This here is primary. This here is primary. Tertiary. This carbon here would be tertiary, secondary, and primary. Okay, so we can identify the different types of carbons. So the hydrogens would be, there would be primary hydrogens here, secondary, tertiary hydrogen. These are primary hydrogens, a tertiary hydrogen, and a primary hydrogen and a primary. So we can also identify the hydrogens. Okay. Okay, let's kind of extend our thinking a little bit on primary, secondary, and tertiary. So what I want to do is I want to go to an example where you have carbon-carbon double bonds, and we'll get to those types of compounds a little bit later. But from what we know with definitions of primary, secondary, and tertiary, we should be able to extend our numbering to those. So this is a compound called limonene. Okay, and we could what we can do is we could go ahead and determine whether each carbon is primary, secondary, or tertiary, or quaternary. But let me first see if I can draw this a little bit better. Maybe if I, well, that didn't. Oh, that's no good. I don't like that one. Let's go back to here. So if I can do this a little bit more carefully. Just doesn't look aesthetically pleasing to me. All right, so there's a carbon here, and it's bonded to one other carbon. So this is a primary carbon. This carbon here is bonded to one, even though it's a double bond, it's bonded to one carbon, 2 carbons. So this would be a secondary carbon. This is bonded to 2 carbons. This is also secondary carbon. this is bonded to 1, 2 carbons, so this is secondary. This is secondary here, secondary. This is tertiary because it's bonded to 3 carbons. This is also a tertiary here. This here is only bonded to 1 carbon, so it's primary. And then this carbon here is primary. Okay, so we can classify this as primary, secondary, or tertiary. Okay, so there's another example that involves carbon-carbon double bonds. Okay.